will also have the opportunity for side individual to become a teaching professor.
In Chinese. Speak in Chinese, right?
Yeah. Today he can very slowly speak. Oh. Today the three phrases and slide up. I don't know why today university student.
我刚有遇到华人，我刚说要上课了，他说好，这样子，我不知道去哪里了。我刚跟他起来。
So can you welcome Professor Saida?
Saida mentor and Linda.
Maybe I just join sometime. If you can speak slowly for your time, then we have the rest time, you know.
Oh yes, I know, Professor.
So, thank you.
Yes, thank you, Professor. Can I?
地上好蛮多玉米的，地上好蛮多的，跟一个碎掉多多。
Hi, good afternoon, everyone. So, as you guys know, my name is Talita. I'm one of Professor Chinghua Ho postdoctoral student. So today, I just want to share my experiment in our lab, and also explain a little bit about capacitance and voltage method, as well as the PN junction. So first, I think you guys already know what is PN junction, right? So basically in semiconductor, we have the P-type semiconductor, and then we also have the N-type semiconductor. But
just need to make a note, okay?
Yes, it's just introduction, Professor, it's okay. So from if we just study of the P-type and N-type semiconductor, it's not really interesting, as you guys know. So how we solve that problem, we combine the P and N-type semiconductor into a P-N junction, what we call as P-N junction. So basically, we just connect the P-type semiconductor here, and then the N-type semiconductor. So when we connect the P-type and N-type semiconductor, as you guys know, the P-type will have more hole, right? More hole, and also an electron here. And then the N-type will have more electron, and then hole also. But when we connect the P-type and the N-type to be a P-N junction, the electron and the hole will diffuse to each other. So it will have a diffusion. So if we draw again, maybe we will have more electron here, and then the hole in the P-type. And then in the N-type, we also will have more hole, because the hole from the P-type will diffuse to the N-type. And we also still have the electron here, right? So in this case, we will have what we call as net charge, positive net charge. Negative net charge here in the P-type, because there is a lot of negative charge from the N-type goes to the P-type. And then on the N-type, on the other side, we will have net positive charge. From the P-type, we get it from the P-type, okay? But in the middle part of it, we will have what we call as depletion region. I think Professor Ho already talked about that a lot. depletion region is where the negative electron here and the positive electron here, like they cannot move to the other part of the p-type or the n-type. It just stay there to become like a junction, you know. So this one what we call as depletion region, or some people will call it as SCR. SCR stands for the space charge region. Actually, we can calculate this kind of width, you know. I think Professor Ho already talked about that a little bit to you. So, but to calculate that one, we need to analyze the band structure of the PN junction first. So, as you guys know, here is P and here is N, right? Sorry. So in the p-type semiconductor, we will have the conduction band. We will have conduction band. We will also have what we call as intrinsic level. And then we will have what we call as Fermi level. And then the last, we will have the valence band. And then from the N-type semiconductor, we will also have the conduction band, we will have the Fermi level, intrinsic level, and also the valence band. I think you guys need to know that in equilibrium, the energy Fermi level of the semiconductor N-type, P-type, of everything is supposed to be in the same level. So it's supposed to be like in the same line. Okay, so from this chart, these things, we can see that there is a gap here, right? The gap here is what we call as the depletion region. So if you want, we can make like a bridge here, like that. And we will get this one, this as a what we call as depletion region. So from this information, we also can get some information that we call as the built-in voltage or VBI. Sometimes we will write it as VBI or built-in voltage. Built-in voltage. Or sometimes we will call it like just like this. Okay. What is the built-in voltage? The built-in voltage is the voltage or the force that the electron needs to go to this barrier, maybe to move here, you know. So it's like, because they will have like some height here, so they need more force, that we call it as a built-in voltage. So basically, we can calculate the built-in voltage. I will tell you how we calculate later. So, as you guys know, you can, I think maybe you already have this kind of equation from your basic semiconductor lessons previously. We can calculate the EI minus EF is equal to, sorry. guys already know that the P-type semiconductor tend to be an acceptor, and then while the N-type semiconductor tend to be the donor, right? So we will get this kind of information.
The EI position need to close to the center of gate.
Sorry, Professor.
EI
Yes.
position
Need
is
to be.
yeah.
Yes, Professor. Sorry. So we can call it this one, right? So I think you guys can notice that the VBI here, the height of this one and this one will be similar with this one. Sorry. Need to be similar with this one, sorry, but because my drawing is not that good, so maybe it looks like it's not similar. But in the reality, it's supposed to be the same height. And then we also can calculate this distance. It also needs to be similar. So from how to this distance can be calculated by how to say that this one plus this one, right?
Yeah.
So we will get this one equal to this one is pretty important equation. Later on, we can use this to calculate the VBI from the data that we got from the capacitance voltage mentioned. So I just want to explain this one to let you guys know about what is VBI and then what is the equation of the VBI that we will use it later on.
NI square.
Oh yeah, Professor, sorry. Yes. So maybe if you want to take a note, you can just take a note first.
So you also can connect the EI in the differentiation region. It will easy to explain why the value is 2 added together, you know?
Oh,
yeah.
So like this,
Yeah.
Professor?
No. Now it connect EI together.
Oh,
only EI.
this
Yeah.
one,
So
yes.
it's parallel to conduction band and the branch band. So the barrier difference should become
The same.
no. This part and this part added together.
Sorry.
Just only.
Yes, Professor, please.
This part.
Yes.
Right?
Oh, yes.
So
yes.
this one added this one.
Oh, yes.
And then this one is this one. And this one is this
Yes. Yes. Maybe we can just.
one. Yeah. So you know the under equilibrium the barrier high is this part and this part added together become
This one. Yes, sir.
So you want to tell a student when 4 bias pentagram and the reverse bias pentagram from here?
I just want to talk.
This is only balance, right?
Yes, Professor, and the balance, Professor. So,
But when you forward, reverse, you want to go?
I didn't go to the forward bias, Professor, only reverse bias.
Oh, reverse. Okay, so from here you want to go reverse. Okay.
Yes, Professor.
Okay.
So. So I think from Professor Hall's previous notes I read from my classmates that Professor Hall already explained a little bit about the metal semiconductor junction, right? So maybe today I just explained a little bit about the PN junction. How to say that, like a diagram to calculate the built-in voltage. As we all know that you guys already know about the depletion region of the SCR, right? So we got something that we call XT or XN here. XT or XN is the depletion region as a certain area. So the XP means that the depletion region at the P and in the P region, while the XN is the change of the depletion region in the N-type side. So from here, we can assume that the junction here is abrupt junction. Abrupt junction means that the transition of the electron from the p-type and the n-type, the hole also, will just like go without any transition or barrier. So we call it like, we assume it's like only abrupt junction. And then from here, we can make a graph. This is the position. And then this is the charge. The charge depend on the position. So from here, because it got the negative charge, we will get the negative charge here. So this is here, and then this one will get minus x. And then at the end side, we will get the positive charge. So we will draw something like this to represent this area as xn. I can call it this one. I can call it as a Q and A, and then this one has a Q and A. So this is if we draw the diagram of the charge. But if we want to draw the diagram of the electric field, it will be like this. So in this area, it will be like no electric field. And then starting from the depletion region, it will go down. And then as it goes to the n-type depletion region, it will go up. And then here it will be 0. So this area, this point, what we call as built-in voltage or E0.
Built-in electrical field.
Yes, sorry.
Voltage is
Yes,
here to help.
built-in electric. So, if you guys read the book, I think the equation already explained well in the book. We will have the Poisson. Oh, I forgot the name. Sorry. From the Poisson equation, we will get this equation. It's already written in the book, so you can, if you have time, you can try to just memorize this kind of equation, because everything we got later on will be based on this equation. So if we derive this one, it will be
Q. Epsilon 分之 Q. Because rho is.
oh yes, I'm so sorry. Yeah, from here we can just delete this one, and then we will get this one left. assumption of minus xp is way less than x and then less than 0. After that, we will, for the built-in voltage itself, we will use this equation. This equation is from the area of this one. We can derive the equation as this one. From here, we can just eliminate the. We can find what we say as E0 because we need that right there, right? So how we know where is the E0 is just multiply that by the XP or ND multiplied by the X. So from here we already define what we call as E0 here. And then after that we will go back to this equation, this one, to put the epsilon 0 inside. extract and then want to know how much is the W, the width of the depletion layer. We need to put it outside and then the equation will become like this. So this is the basic equation of the depletion region. But here we also have a different kind of situation. So first, if the NA is way bigger than the NB, the equation will be like this. And then if the NB is way bigger than the NA, the depletion region will be this is the equation that we will use later on the capacitance voltage measurement. So maybe you guys can write first. I think maybe some of the explanation is not quite clear, and then maybe can ask Professor Ho for more detailed explanation.
Right career. Oh, you just let me do this.
I'm afraid something is not clear, Professor.
So EG equal to this one. So NASP equal to NDSN.
Yes.
So this is why.
Some of them maybe I'm not pretty clear, Professor. Yes.
So if SN equal to ND and SP.
Yes.
And then the total width is SN and SP
Plus XP.
plus together. So you can become SN is SP. So you become ND NA SP. Oh.
Yes. Yeah, that's what is right from this.
So you want to go SP, you will become width. SP, you will become ND, NA, and SN width, total width, but you need to which side you will see this one. Right?
Yeah.
So you will the differentiation of the N region will depend on the whole topping concentration. And this is the P side either to depending on the ND topping concentration. But here, people want to know what become this one. Oh. It's S10, right?
Yes.
So SP, we need to check how they come here.
Yes, Professor, I will.
I tweet out. But now, this one will tell people the
Yes.
N side depression unit depending on
Yes.
A bar. The QND is S1, right?
Yes.
This is correct one. This is correct one. Our
That
open.
one is correct, Professor. From my notes, it's correct, Professor.
So, it says here, this one and this one the same, right? Why does say this part and this part all equal to E0 or to the plasma field? So that is why this one and this one the same. But this equation can determine which side depression width is determined by the concentration ratio. But you need to let the student why the depression width is this is E0.
Yes, Professor. From here, Professor.
This one.
Yes.
This is E0 double.
Yes, Professor.
So it's no problem.
Yes, from the E0W and then just substitute the XP with what Professor already write, and then we can get it like that.
So the totally
Yes, Professor.
the width is determined by both sides, and both sides determined by width ratio of the concentration.
Yes.
If the P side determined on the N top,
No.
the N side determined on
The
the P top.
isopropyl, yes.
So you can continue.